Welcome to the Problemics channel, Season 1, Episode 7, the episode in which we will dissect the solutions of the problems S1M6, S1M7, and the solution of the problem S1M8. We will begin our discussion with the solution of the problem S1M6. As a reminder, the objective of the problem S1M6 was to find the shape, the length, and the number of shortest possible paths between two diametrically opposite vertices of a regular octahedron. For example, for demonstration purposes, in this particular case, I have named these vertices as A, B, C, D for logically the horizontal cross-section of the octahedron. The logically top vertex of this octahedron I named as E, and the logically bottom vertex of this octahedron I named as F. Consequently, the objective in this particular situation is to find a shortest possible A to C path that an ant, for example, our friendly inquisitive character here, can take over the outer surface of the given octahedron from the vertex A and arrive to the vertex C. This problem is a typical representative of a difficult to solve problem because in 3 space it's not really clear how exactly that shortest path from A to C should run. And even if we can somehow concoct such a path, it still remains to be seen if we can generate a convincing story or a convincing line of reasoning that this particular path is the shortest possible across all the other possible paths over the surface of regular octahedron from A to C. Now, in Season 1, Episode 1, we claimed that mathematics, first of all, is an art. It is an art of telling a story of how and why. Consequently, behind every worthy and interesting mathematical problem, there sits a story which explains how and why. And our objective is to uncover or generate that story. During that process, we claim that we put our mind into a mode that is faithfully close to the mode in which the mind of a practicing mathematician operates, because from the outset, stepping into such a problem, we do not really know which particular solution or which particular method or way will work. Consequently, we try and fail several times before we succeed, and it is that process of trial and failure is what constitutes doing mathematics or studying and learning mathematics. In Season 1, Episode 4, we explained the mechanics of the transform and conquer problem-solving approach. And the viewers who follow our program already know that in this particular case, it is a good idea to begin experimenting with putting together the models of a regular octahedron out of paper, as I've done over here. I did this particular model using 2 colors, but you can experiment with trying to make a regular octahedron in which every face has a different color. And in this particular case, it turns out that amongst many possible nets of a regular octahedron, for example, this particular one helps us solve the problem according to the transform and conquer problem-solving approach, which we know instructs us to look for a transformation that possesses 3 fundamental properties. Such a candidate transformation should be reversible or invertible. That transformation should preserve the technical essence of the problem at hand, and that candidate transformation should provide us with a tactical advantage. Consequently, in this particular case, we execute 5 cuts of a regular octahedron, and because, for example, if we make a model of a regular octahedron out of paper and study its structure, we see that at each and every vertex of a regular octahedron, how many distinct planes or how many distinct faces meet. Correct. At every vertex of a regular octahedron, precisely 4 distinct planes or 4 faces meet. For example, for this particular vertex of a regular octahedron, we have this face, the front face, the side face, the other side, and the back faces meet. And what does it mean? It means that when we open such an octahedron into a corresponding net, then any one specific vertex, depending on the cut, will be split into at most 4 distinct copies of itself. In this particular case, we executed, as I said, 5 cuts, and as is evident from this particular net, these cuts were placed along the edges DE, which is evident by this side right here, DE, DF, DF, DA, which is this one, DA, DC, this one right here, DC, and this one right here, and the 5th cut was made along the edge BC, or this one. It should be evident that 2 faces of our solid meet or share precisely one edge. Consequently, if we place a cut with a mathematical knife along that particular edge, this edge will split in precisely 2 copies of itself. For example, as shown here, the edge BC here and the edge BC here. Now, is this transformation of cutting a given solid into its net reversible or invertible? The answer to that question is yes, of course, because if we used a mathematical knife to cut our solid open into a net, we can fold that net back into the original and use a mathematical glue to put the solid back together. For example, over here, I made a small model of a regular octahedron. There it is, from different angles, if you guys can see it. And this particular model opens up like so, according to the 5 cuts that I already explained, like so, into a shape that is somewhat reminiscent of a snowflake of sort. Also notice here that I used flaps, but you of course guys understand that the flaps are not a intrinsic part of a net of a solid. They play solely a utilitarian function because we put the glue on these flaps when we put this solid together, and to make sure that, or prove that this transformation is reversible, we put it together like so, glue the flaps, and our solid becomes the original one. Does that transformation preserve the technical essence of the problem at hand? The answer to that question is yes, again, because in this particular case, we managed to find a such net that allows us to connect the origin point A, shown here, which is this vertex right here, and the destination vertex C, shown here and here, with a straight line, which, as we know, is a minimizing geodesic in the Euclidean space and in the Euclidean plane. And at each and every point, that straight line that connects the vertices A and C runs over what? At each and every point, that straight line that connects the origin vertex A and the destination vertex C, that line runs precisely over the material of that net without stepping out into the ambient plane or ambient 3 space. Consequently, when we put, as I demonstrated earlier, that solid back into its original form, then that particular path that we traverse from A to C here or from A to C here will lie or run precisely over the outer surface of the solid as requested in the problem statement. Lastly, does this particular transformation allow us a tactical advantage? And the answer to that question is again, yes, of course, because if in 3 space it was not really clear how to connect the vertices A and C over the outer surface of the given octahedron, in the transformed and such easier in some sense problem, we can connect the points A and C in such a way that each and every point of that line runs over the material of the net, and because we use the minimizing geodesic in the Euclidean plane, that precisely guarantees the minimality of the length of this particular path, and in some sense this is precisely what the Euclidean straight edge was born. Consequently, let me use, for example, 2 colors, yellow and blue. We see that we can connect the point A and C like this, and the points A and C like this. Now, what do we see over here? Well, we're told that the particular solid that we're working with is a regular octahedron, which means that each and every face of this octahedron is an equilateral triangle that has its side length A, a generic representation of the length of a side of such a triangle. And that means that every side of these triangles has one and the same length A, which means that, for example, the shape A, B, C, E is a rhombus. In that rhombus, the edge BE plays the role of one diagonal, and our solution path AC plays the role of another diagonal of a rhombus. It is known from plane geometry that the diagonals of a rhombus meet each other at right angles, like so, and these diagonals cut each other in half. In other words, let's say the point where the straight line AC and BE intersect, we will name that point as M for middle, for example, like so. Then we will be able to say that the length, for example, of the line segment MB is the same as the length of the line segment ME, and that length is precisely A over 2. Now, what is the length of the line segment AC? Well, that question can be answered in a straightforward manner, because now we have, so for example, a right triangle AMB, and from the right triangle AMB, it follows what? By the Pythagorean theorem or Euclid's Elements, Book 1, Proposition 47. We have it that the length AC is equal to the square root of, for example, let's say not AC but AM, is the distance AB squared minus AB squared minus distance MB squared. Now that means that the distance AM, or the distance, AM over here, equals to the square root of AB is A square, and MB is 1/2 of A minus A square over 4, and that is equals to A square root of 3 over 2. Consequently, the entire length AC is equal to twice the length of AM AM, and that distance is precisely a square root of 3. And now we answered one part of the problem. We know the length of the minimal path from A to C in terms of the length of the edge of the given octahedron, and that is the length of that edge scaled by square root of 3. Now let's analyze what these paths of minimal length between the vertices A and C will look like on the solid. For example, let's concentrate on this blue path right here that runs through the faces ABE and BCE over the edge BE. Where is the edge BE on our solid? It's this guy right here. So in the middle of that edge, there will be point M, and our ant will crawl over this face from A to M and then dash for the vertex C in a straight line again. This will be one path. The second path will run over the edge BF. Where is that edge on our solid? This is the edge right here, BF. Consequently, we mark the middle of the edge BF and we draw a straight line from A to that point M, and then from M it's a victory lap to the point C. So this gives us two distinct paths of minimal length from two diametrically opposite vertices of a given regular octahedron A to C. However, we see that once we obtain this, for example, sample pair of solutions in case of a net, and we put the solid together, then it becomes possible to ink an algorithm according to which we can solve this particular problem completely without opening the given solid into its net. How does this algorithm work? Well, it should be evident. Let me take two different colors, for example, pink and green, that with respect to a chosen departure vertex, for example, vertex A, on the outer surface of a given solid, there exist how many opposite, in some sense, edges to the middles of which our friendly and inquisitive ant is supposed to crawl? Well, there exists 4 such edges. 2 of these edges we already covered, BE and BF, and another 2 such edges will be DE, this guy that we cannot really see, that's why I show him in the dashed line, and the edge DF. Consequently, we draw these paths by marking, for example, the middle of the edge ED or DE like so, and we draw a dashed line like this, and then from the middle point the straight line to the vertex C, and in pink, for example, we mark the middle of the edge DF like so, and the fourth and the final distinct shortest path from A to C will run from A to the middle of the edge DF, and then from the middle of the edge DF straight to the point C right here. And we managed to solve this problem completely, again using the transform and conquer problem solving approach, in which the solution of the transformed problem, the problem that is embedded into the Euclidean plane, became easier or more straightforward in some sense, and then we reverse transformed the solution of the transformed or easier problem into a solution of the original problem, and we recovered the length of the shortest path from 2 diametrically opposite vertices of a regular octahedron, which is given by the length of an edge of that solid scaled by square root of 3. We covered the shape. We know exactly how these paths run over the outer surface of a given solid, and we know their number, 4, which are shown over here in blue, yellow, pink, and green. done slightly more precisely or slightly more professionally with a tool called GeoGebra, this particular solution will look as follows. Now that we solved the given problem S1M6 completely, we remember that a correct way of practicing mathematics that we explained in detail in Season 1, Episode 2 suggests that we should reflect on our problem-solving experience and analyze the points where we got stuck, why we got stuck, and how we can overcome these points of contention. And we should also step back and take a 1,000-mile view at the particular problem and try to generalize and abstract it further if we can. We also remember that in mathematics, you're not only allowed, but you're encouraged to ask questions, which means that once we know the specific shape of all the minimal paths between two diametrically opposite vertices of a given regular octahedron, we may analyze the properties of these solution paths, just like we did it in the previous problems. I will not go over all the possible details of these properties, but for example, one such property you should see right away, and that property is the symmetry of a solution path. For example, a shortest path that is blue from here to here and to here, in other words, a shortest path from the vertex A to the vertex C, is also, due to the symmetry of this particular situation, will be a shortest path from C to A in the opposite direction. Also, we see that if we glue two opposite, in some sense, two such paths, for example, if we traverse the outer surface of the given regular octahedron from the point A over the first blue leg, over the second blue leg into the point C, and then we crawl from the point C over the pink leg here and then here, we in some sense will circumnavigate this particular regular octahedron or make a round trip from the vertex A to C and from the vertex C to A. However, we will not visit all the faces of the given regular octahedron, but we may inquire, for example, if we cut this particular regular octahedron along this plane, if you guys can see, let me try to, this guy right here, this plane that cuts across the given regular octahedron, we may inquire, will this particular cut partition the given solid into two smaller or sub-solids, and we wonder if the volumes of these particular sub or smaller solids will be the same, and whether the volume of each half is exactly 1/2 of the volume of a given regular octahedron. From the solution of the problem S1M5, we remember that our hunches and wishful thinking will remain forever and ever just that, hunches and wishful thinking, because the way in which mathematics works is that these hunches and wishful thinking is converted into solid mathematical facts only when we present a correct, valid, and legal proof of our hunch, or we present a proof that this hunch is not correct and we thus refute it, and we leave this as an exercise for you guys. Think if this particular cut partitions the volume of a given regular octahedron into two equal halves. Meanwhile, we will move on to the solution of the problem S1M7. As a reminder, in the problem S1M7, we're given a regular tetrahedron with the edge length of 20. Every edge in this tetrahedron has the length of 20. For demonstration purposes, I named that particular tetrahedron as follows: A, B, C, and D. And again, for demonstration purposes, from the vertex of this tetrahedron D, a height or an altitude of the triangle ABD is constructed in such a way that it meets the edge of the tetrahedron AB at the point G, and another altitude or height of the triangle ABC is constructed from the tetrahedron's vertex C onto the base of the triangle AB, which is also lands at the point G. Consequently, on the line segment DG, we're given the point E that is displaced from the vertex D by 7 units of distance, and on the line segment CG, we're given the point F that is also displaced from the vertex C by the same distance of 7 units of length as shown over here. The distance DE equals the distance CE, and both of these distances is 7 units of distance. The objective of this particular setup is to find the length, the shape, and the number of the minimal in length paths over the outer surface of this particular tetrahedron that our friendly inquisitive ant can take from the point E somehow to the point F. Those of our viewers who have been solving similar problems in the past already feel that because specific numbers are given, such as 20 and 7, that means that this problem is a deviation in some sense from the previously solved problems. In general, no one in mathematical community cares about these specific numbers, but everyone in mathematical community cares about the story of how and why that sits behind this nice and beautiful little problem, because there is a reason why these particular numbers were chosen and why this particular problem was designed and put together in the first place. The lesson that we learn from the solution of this problem is the following. Our everyday common sense intuition is a very not reliable partner in mathematics when it comes to manipulating seemingly obvious or straightforward observations. In other words, a lesson that we draw from solving this problem is that it's laughably easy to run into trouble in mathematics if we manipulate the said obvious or straightforward observations without proper care. For example, every time I give this problem to certain students, invariably some number of students run into one and the same trap, because the reason roughly as follows. Roman, you keep talking about all this minimizing geodesics, minimizing geodesic this, minimizing geodesic that, Euclidean space, Euclidean plane. Here you told us that the distance from the point D to the edge AD, being a perpendicular projection, is the shortest one. It's a minimizing geodesic, so the distance between the point D and G is minimal in some sense. Also, you're telling us that the distance from the point C to the point G on the edge AB is also minimal in some sense. You told us that the origin point E and the destination point F also sit on these minimizing geodesics. Consequently, we think, or we claim, that a solution path in this particular problem should be obviously or straightforwardly a sum of two line segments of minimal length. In other words, the distance from EG will be the first leg of the solution trajectory, and the leg GF from here to here will be the second leg of that solution path, precisely because the sum of two minimal lengths should minimize the distance sought after. However, that is precisely the crux of this particular problem. Is that reasoning valid, and is that conclusion correct? Is that really so that the sum of two minimal, in some sense, distances will provide the minimal distance sought after on the given solid A, B, C, D? Well, in Season 1, Episode 4, we explained the mechanics of the transform and conquer problem-solving approach. We know that according to this approach, we should look for a transformation that is reversible or invertible, that preserves the technical essence of the problem at hand, and that provides a technical advantage. From the solution of the previous problems, we also know that a given convex polyhedron, of which a regular tetrahedron certainly a representative, can have multiple distinct nets. Consequently, when we look for a successful or for a fruitful net of a particular solid that may help us solve the problem at hand, we may shuffle or go through several such nets until we settle on a winning one. In this particular case, it turns out that a net of a given regular tetrahedron that looks like a large equilateral triangle is actually a fruitful one. We know that given a regular tetrahedron, at each vertex, such as this one for example, how many distinct planes meet? Correct. At each vertex of a regular tetrahedron, precisely 3 distinct planes or 3 distinct faces meet. That means that given a particular cut of a tetrahedron at hand, any one of these vertices may split in up to 3 distinct copies of itself. And in this particular case, we see that that is exactly what happens to the point A, because how many cuts do we make for this tetrahedron in order to produce this particular net? Well, we make 3 cuts along the edges A, C, as is evident over here by these 2 line segments A, C, and AC. We cut this tetrahedron along the edge A, B, as is evident by these 2 edges AB and AB. And we also cut that tetrahedron along the edge AD, as is evident by these 2 edges right here, AD and AD. Consequently, when we open up these 3 faces like a flower of a regular tetrahedron into a net, then the vertex A splits into 3 distinct copies of itself, shown here, here, and here, and I did not bother with naming these vertices A prime, A prime. You guys understand what is going on here. Consequently, in this particular net, the points E, the departure point E, and the departure and the destination, point F, will be located on the heights of the triangles ABD and ABC, as shown here and here. And we know that that particular transformation where we step down from the 3 space into the 2 space is reversible, because we can always fold that net and glue it back into the original solid. That particular transformation preserves the technical essence of the problem at hand, meaning that that particular transformation preserves the essence of what does it mean to be a regular tetrahedron. And this particular net also provides a technical advantage, because the points E and F can be connected with a minimizing geodesic. Let me use the green color, for example, in such a way that each and every point, that minimizing geodesic, runs precisely through the material of the net and doesn't step out into the ambient 2 space or the ambient 3 space. Consequently, because the points E and F are displaced from the base AB or DC by equal amounts correspondingly, in other words, the distance EG is the same as the distance FG, and likewise the distance from E to D is the same as the distance from F to C, it follows that the solution path, or a solution path E to F, will run parallel to the edge DC and the edge AB. Consequently, that will be one shape. And what is the length of that minimal path? Well, the height is also a median in this particular case, because ABD and ABC are equilateral triangles. They have exactly the same size, so the length of the line segment EF will be what? 10 plus 10, 20. So we claim that the length of a solution path will be precisely 20. Now let's go back to the students who claim that the sum of the two legs EG and GE will be a solution path, and we will crunch some numbers and verify, is that so? In this case, all we have to do is observe that the distance from the point E to the point G, this distance right here, is very easy to recover because it will be equal to the distance from the vertex D to the point G, the distance dG, minus the distance from the point D to the point E, which is given to us, 7 units of length. So the only length we have to recover in this case is the length of the height of the triangle ABD or DG. That length can be recovered straightforwardly via the Pythagorean theorem, which says that the length of the side DG will be equal to the square root of 20, the length of this edge right here, AD squared, which is 400, minus the square of the length AG, which, as we know, 10 units of length right here. So 10 squared is 100, 400 minus 100, 300. Square root of 300 is 10 scaled up by square root of 3. Consequently, that distance from E to G will be given by the square root of 3 times 10 minus the length of 7 that is given to us, and the legs EG and GE put together, because they're of equal length, will be 20 times square root of 3 minus 7 times 2 minus 14. And the interesting question becomes, in what relation less than, greater than, or equal to numbers 20 times square root of 3 negative 14 and 20 have? What is the relationship between the magnitudes of these two expressions? That question is easy to resolve. We simply move 14 or add 14 to either side of this investigative relationship and obtain 20 scaled by square root of 3 versus 34, 20 and 14, 34. If we square both sides of this relation, we get 400 times 3 versus 34 squared. 34 can be represented as 20 plus 14 as shown over here. These numbers are easy to square. 20 squared is 400 times twice the product between 20 and 14 is 40 times 14 plus 14 squared. 14 squared, we remember from the first grade multiplication table, 196. 40 times 14 is 560. 560 and 400, 960 plus 196 comes out to 1156. And now 400 times 3 is 1200. The question is easy to answer. 1200 is most certainly larger or greater than 1156. So the students who originally thought that a solution path of this particular problem consists of two legs, EG and GF, made a mistake, and perhaps that was one of the reasons why this problem was designed in the first place, to show how laughably easy it is to run into trouble in mathematics by manipulating obvious or straightforward observations without the proper care. Now let's analyze the solution path that we acquired over here. How many legs will this solution consist of? This particular solution from E to F will consist of 3 legs. The leg that runs over face ABD from here to this point. On the actual tetrahedron, what this leg will look like? Well, that leg will look like so. It will run parallel to the side AB right here and to the point on the edge DB right here. At this point, our ant will, so to speak, turn the corner and crawl along the face BCD or BCD, parallel to what? parallel to the edge DC, which on the actual solid is shown here. So that part of the trajectory will look like so. That will run into this point on the edge BC. This is this point right here on the edge BC. This point corresponds to this point. And this was the second leg of the winning journey. And the third and the final leg will run from this point on the edge BC into the destination point F, parallel, again parallel, to the edge BA, in this direction from B to A and to this way. So the direction of this particular path will run here like this and like this. But is that the only possible solution of this problem? We see that no, that is not the only possible solution. Our end can also crawl over the face ABD, or over the face ABD here, in the opposite direction this way, into the parallel to the edge AB into this point, or on the actual solid, the first leg of that second winning orbit will run like so, parallel to the edge AB into the point, this one on the edge DA, and if we scale it up, it will represent, this point will be represented here. The second leg of that winning journey will run over the face ACD, or ACD over here, parallel to the edge DC, again this way. So that particular straight line will run parallel to the edge DC on the other side, into this point, or this point right here. And the third and the final leg of this winning journey will run from this point in the plane ABC into the point, destination point F. So here it will run in this direction, and in this direction, like so. Shown a little bit more precisely, this particular path constructed in the free software GeoGebra will look as follows. Very nice. Now that we have solved this particular problem completely, we know the length, 20, we know the shape, we know the algorithm according to which the solution path can be constructed given a copy of this tetrahedron without opening that solid up into a net. The solution is shown here, like this and like this. And we know that this particular solution has two different paths. The green path shown over here and the pink path shown over here. Now, before we wrap our experience and the work with the solids and begin addressing the solution of the problem S1M8, I would like to potentially expand your mathematical and intellectual horizon by saying a few words about the Platonic solids that we worked with, but that section is optional. Feel free to skip it and fast forward to the solution of the problem S1M8. So far, we have worked with a regular tetrahedron with a cube. We also worked with a regular octahedron, and these three convex polyhedrons are known as Platonic solids, and there exist several different proofs that in the Euclidean 3 space only 5 such Platonic solids are possible. The remaining 2 Platonic solids that we haven't worked with are a regular icosahedron and a regular dodecahedron. For example, a regular icosahedron is made out of equilateral triangles, but the number of equilateral triangles that goes into the production of a regular icosahedron is way larger than the number of equilateral triangles that goes into the production of a regular tetrahedron. One way to make sense of a regular icosahedron is to look at it as follows, using the model that I put together, using three different colors, in which the, for example, top and bottom shapes represent the polar caps, so to speak. For example, this one can be the north polar cap, and the bottom one can be the south polar cap, and the equatorial belt shown in orange. But again, this is purely logical, purely for demonstration purposes, because this particular solid is fully symmetric in some sense. It doesn't have any preferred edges, vertices, or faces. This is just one way to make sense of this particular Platonic solid. Also, here in this particular model of a regular dodecahedron, I use two different colors, which roughly partition this particular solid into two different shapes, like so, or like so. And for the purposes of studying the theory of groups, it is actually helpful to put together all these solids, including a regular dodecahedron, using a different color for every face of the solid. Now, when the theory of groups looks at these particular 5 Platonic solids, it actually sees only 3 such solids. How can this be? Well, the reason why the theory of groups looks at 5 Platonic solids but sees only 3 can be explained by the notion of duals of these polyhedrons. In particular, let's say we have a cube whose vertices we named as A, B, C, D, and E, F, G, and H. Every polyhedron, such as a cube, for example, has only 3 distinct or 3 basic building blocks, which I designated with the letters V, E, F, where the letter V stands for vertices, such as A, B, C, and D. The letter E stands for the edges of a regular polyhedron, such as edge EA or AD, for example. And F stands for a face of a polyhedron, such as, for example, the facade or the frontal face AEHD. In order to study the structure of these particular solids, mathematicians introduced the notion of incidence. For example, 2 building blocks of a polyhedron are said to be incident if one of these building blocks participates in the formation of the other, and if one of such building blocks does not participate in the formation of the other, then these 2 building blocks are not coincident. For example, the vertex A, for example, of this particular cube is incident with the edge AD, because precisely the vertex A participates in the formation of the edge DA. Likewise, the edge DA, for example, is incident to the face AEHD, because the edge DA delineates the side of this particular face. However, the edge DA, for example, is not incident with the face CBFG, or the back plane of this particular cube, and so on. Consequently, now that we understand what the fundamental building blocks of a polyhedron are, we can give a definition of what does it mean for 2 polyhedrons, P1 and P2, to be the dual images of each other. In detail, 2 polyhedrons, P1 and P2, are the dual images of each other if it is possible to establish a bijection between the respective pairs that are incident in both polyhedrons, in such a way that the faces of the polyhedron P1 are mapped to the vertices of the polyhedron P2. the vertices of the polyhedron P1 are mapped to the faces of the polyhedron P2, and the edges of one polyhedron are mapped to the edges of the other polyhedron. According to that definition, for example, the dual image of a regular tetrahedron is another regular tetrahedron. For example, the centers of the faces of a regular tetrahedron play the role of the vertices of another regular tetrahedron that is inscribed into the outer or the parent tetrahedron. That idea, captured with the free software called GeoGebra, can be rendered as follows. Likewise, according to the definition of dual polyhedrons, it turns out that a cube and a regular octahedron are the dual images of each other, which precisely means that a cube can be inscribed into the regular octahedron in such a way that each and every vertex of a cube rests at the center of the corresponding face of a regular octahedron, and conversely, a regular octahedron can be inscribed into a cube in such a way that the centers of the faces of the cube play the role of the vertices of a regular octahedron. Rendered in a more professional and precise way with the software called GeoGebra, that particular situation will look as follows. Lastly, according to the definition of dual polyhedrons, it turns out that a regular dodecahedron and a regular icosahedron are also the dual images of each other, which means that, for example, a regular icosahedron can be inscribed into a regular dodecahedron in the same way as we explained before, and conversely, a regular dodecahedron can be inscribed or placed inside of a regular icosahedron in a way that we explained before, and rendered in a more precise and professional setting using the free software called GeoGebra, that particular effect will look as follows. Also, in order to make these ideas that we just covered more systematic and more easy to comprehend, I put together the following table that correlates the duals that we discuss right now: a cube and a regular octahedron, and a regular dodecahedron and a regular icosahedron. Now that we understand what dual images of each other mean in the context of polyhedrons, we can pose the following question. If we take, for example, a regular tetrahedron, and if we take a cube, we may inquire which particular object in this particular case is more symmetric than the other or less symmetric than the other. What do you guys think? How can we answer that question in an objective way? Well, it turns out that the theory of groups provides one way to answer that question using the notion of rigid symmetries. If you remember from previous episodes, for example, if we take a regular tetrahedron and imagine that through its vertex over here there passes an axis of rotational symmetry, then the rotation of a regular tetrahedron around that axis by 120 degrees will place or bring that tetrahedron back into coincidence with itself. That particular rotation becomes an element of a group of rigid symmetries of a regular tetrahedron, and it turns out that that particular group is isomorphic to the symmetric group S4, and the cardinality of that particular group is given by the factorial of the subscript in this case. 4 factorial is 24, which means that the group of rigid symmetries of a regular tetrahedron contains 24 elements. Likewise, now that we know that a cube and a regular octahedron are the dual images of each other, both of these solids have the group of rigid symmetries that consists of 48 elements. And the group of rigid symmetries of a regular icosahedron and dodecahedron can be, this is a slightly technical detail, represented as a direct product of the alternating group A5 and the finite cyclic group C2, and as such the cardinality of this group will be 120 elements. Now, before I said that when the theory of groups looks at these 5 Platonic solids and it sees only 3, what does that mean? That means that precisely through the connection of the fact that certain Platonic solids are the dual images of each other, that means that, for example, a specific congruence motion of, let's say, a regular dodecahedron translates into unique congruence motion of its dual image of icosahedron, and conversely, a particular congruence motion of a regular icosahedron translates into unique congruence motion of its dual image or a regular dodecahedron. That is why the groups of rigid symmetries of these particular solids are organized in this particular way. And now we have a meaningful or an objective way to compare the amount of symmetry in these particular solids. As such, we see that, for example, a cube and a regular octahedron are twice as more symmetric in some sense as a regular tetrahedron, because there are 24 elements in the group of rigid symmetries of a regular tetrahedron, and there are twice as many, or 48 elements, in the group of rigid symmetries of a cube and of a regular octahedron. That means that one and the same solid, such as a cube, for example, can be brought into coincidence with itself in 48 different ways, while a tetrahedron can be brought into coincidence with itself in 24 different ways. But across these 5 Platonic solids, the cardinality of the group of rigid symmetry of a regular icosahedron and dodecahedron is the largest one. It contains 120 elements. Consequently, in that sense, a regular icosahedron and a regular dodecahedron are more than twice symmetric as a cube and a regular octahedron across these 5 Platonic solids. Now, before we call it quits with the Platonic solids at hand, I would like to mention the fact that because we're studying mathematics, it doesn't really mean that we have to stay with a purely mathematical content. I suggest that, or it is a good idea if you guys experiment with these Platonic solids more on your own. As an example, to give you several ideas, here I covered a surface, the outer surface of a cube, with glue, and then covered it with glitter, and voila, we have a nice little party cube, which is a Platonic solid covered with glitter or fairy dust, as an example. As another example, over here I have a cube again with a particular pattern that is carved on each and every face of that cube. And even though I made this cube out of heavy paper, it is possible to place a nice little light inside a cube and make a lantern or a decorative pattern for a tree or for your house. And of course, your imagination is the limit over here, because types of patterns that can be cut on the faces of this polyhedron is great. And for example, a lantern that is made in the shape of a regular icosahedron may look very, very nice if we imagine that each and every face of that particular solid has a certain interesting pattern carved in it and a nice little light is placed into it. Lastly, we can also make it so happen that our cube, for example, gains a friend in the shape of a butterfly, and these two guys become close friends. If you guys can see, maybe I can come a little closer this way. And maybe it can so happen that this larger butterfly has a smaller friend that looks as follows, and our cube can also have a friend that is a smaller butterfly. Again, your imagination is a limit. Experiment away, and enduring this experimentation is precisely how we study mathematics deeper. In the final segment of this episode, we will dissect the solution of the problem S1M8. As a reminder, in this problem, we're given a 3x3 chess board and we're given two pairs of chess knights of opposing colors. For example, we're given two white chess knights and two black chess knights. Certain number of things in this problem do not really make much of a difference. For example, for demonstration purposes, for this 3x3 chessboard, I used 5 dark squares and 4 light ones. But the essence of this problem will not change if we use 5 light squares and 4 dark ones. Also, the initial configuration of the chess knights also is free because for demonstration purposes, I put 2 white chess knights on the top and 2 black chess knights on the bottom. But the essence of this problem will not change if we put the black chess knights on the top and the white ones on the bottom. Also, it doesn't really matter if we align our chess pieces horizontally because we can as well align them vertically like so, and by aligning them vertically that will not change the essence of the problem as well. However, for demonstration purposes, given this particular configuration, the objective is to swap these anonymous positions of the anonymous chess knights in the smallest number of legal chess knight moves possible. Again, in this particular demonstration case, our objective is to make sure that the 2 white knights that are positioned in the top row of the 3x3 board are located at the bottom row, and at the same time, the 2 black chess knights that are positioned at the bottom row of this 3x3 board are located at the top row in the smallest number of moves possible. Now, it may seem that this problem is worded very differently from the problems that we've been solving previously, the problems that dealt with regular polyhedron, but because this problem is placed in the same sequence of problems which can be solved using the transform and conquer problem solving approach, it is evident that a successful, or there exists a successful transformation that unlocks a elegant and a beautiful solution of this problem. Now, what this transformation may be. Upon thinking about this problem for some time, and most likely trying and failing several times, we may realize that this problem has actually very little to do with chess and pretty much everything to do with one of the fundamental notions of the theory of graphs called graphs isomorphism. Speaking of graphs, I would like to bring you guys back for just one moment to the study of the regular polyhedrons that we looked at in the previous episodes, and mention that one of the several reasons why these polyhedra should be studied is because, for example, the graph of the finite symmetric group S4 on two generators, while technically a truncated regular octahedron, still has as its carcass or as its foundation a regular octahedron, and rendered with the free software called GeoGebra, it will look as follows. Likewise, one of the reasons why it's a good idea to study the structure and the properties of, for example, a regular tetrahedron is because a graph of the finite alternating group A4 on two generators, while technically a truncated regular tetrahedron, still has a wholesome regular tetrahedron as its carcass or as its foundation. Rendered with a software called GeoGebra, such a graph may look as follows. The gray dots that you guys just saw on the previous pictures are referred to as the nodes or the vertices of a graph, and the blue and the red line segments that connect these vertices are referred to as the edges of a graph, or sometimes these edges are directed when they carry an arrow that points in this or that direction. Now, technically, two graphs from the theory of graphs are called essentially the same or isomorphic if between the sets of vertices of these graphs it is possible to construct a bijection that honors the following constraint. Whenever two vertices in either of the graph are adjacent, then the corresponding two vertices in the other graph are adjacent as well. That definition is fairly small, concise, and easy to comprehend and easy to remember, but as an informal exercise, I invite you guys to first decide on your own which pair of these two graphs are isomorphic or essentially the same, and which of these pairs of two graphs are not isomorphic. Well, according to our definition of two essentially the same or two isomorphic graphs, the graphs shown on the top over here, the green one and the red one, are actually isomorphic, and the two graphs shown over on the bottom over here are not isomorphic. Now, how can we make sense or develop some intuitive grasp, intuitive understanding of what does it mean for two graphs to be essentially the same or for two graphs to be isomorphic? Luckily enough, in the theory of groups, there exists a quite nice model that explains or showcases the idea of graph isomorphism, and that model is known as balls and strings. In that model, the vertices of a graph, like this ones, for example, E and B, are modeled with a billiard ball or a tennis ball or a golf ball. It doesn't really matter. A small round object becomes a model of a node or a model of a vertex of a graph, and the model of an edge of a graph, such as the line segment that connects vertices E and B over here, for example, becomes a string or a rubber band that can be stretched and contracted. Then let us conduct the following thought experiment. Let's say we grab two vertices or two nodes of a graph connected with an edge, and then we begin stretching and pulling them apart, for example, or bringing them together, or manipulating them let's say in the ambient plane or even in the ambient 3 space, any which way we want, as long as we do not break, rip, or tear apart the rubber band that connects these two balls. As we do so, imagine further that we take photographs of the intermediate configurations of these three objects. And then the theory of graphs claims that as long as we do not rip, tear, or break the band that connects these two balls, all the intermediate configurations that we snapped with our photo camera are actually identical as far as the theory of graphs is concerned, and consequently the graphs that are portrayed on these photographs are essentially the same or isomorphic. Now, what does this idea of graph isomorphism has to do with our problem where we have chess knights sitting on the chessboard? Again, if we carefully think about it, then a successful transformation that unlocks an elegant and quite beautiful solution of the problem can be obtained as follows. Let me take this larger figures off because we will be drawing pretty soon on these squares and using them for something else. And let us do the following. Let us pick one square on this board. Which one doesn't matter as long as it's not the center one. We have 8 choices for the initial square. Let's say I'll pick for demonstration purposes this one, but you guys are more than welcome and you really should experiment with picking a different square for an initial one, and we number this square as 1. In this particular case, this number 1 or this point is a node of a graph that represents this particular square of a chessboard. Then again, once we pick one initial square, we have 2 choices for one and the same consistent direction. We can travel around the given chessboard with the legal moves of a chess knight counterclockwise or clockwise. Let's say, for example, for demonstration purposes, I pick initially the clockwise direction. If we have, let's say, this chess knight position over here, what will his next move be clockwise? Of course, he will jump this way in the L shape or this way, but this chess knight will arrive at the square that we will number as 2. And again, this particular small dot represents a chess square positioned over here, and that point will become a node of a future graph. And we continue likewise numbering the next legal moves of a chess knight on our board. After the square number 2, where will the knight jump next? It will jump over here. We'll number this guy as 3. After this square, continuing in the clockwise fashion, the chess knight will jump to the square number 4, this one, traversing an L-shaped trajectory. From the square number 4, it will jump to square number 5. We'll mark this guy as number 5. After the square number 5, the knight will jump where? It will jump over here into this square, which we will mark as number 6. After that square, it will jump to square number 7. We will mark this guy over here, number 7. After the square number 7, the knight will jump in this direction clockwise into the square over here. We'll number this guy number 8. And after the square number 8, the chess knight will close its trajectory, will close its orbit, and it will jump back to the square number 1. Technically, if we continue to number our squares the same way, that should be 9, but in this case it should be evident that we're operating in the land of modular arithmetic, modular 8. So instead of 9, it will be square number 1. Now, we remember that the shape of the edges between the nodes of a graph in the theory of graphs is also irrelevant. For example, this particular graph on, let's say, 3 vertices positioned any which way, and the same 3 graphs positioned on a circle, for example, and numbered and or named consequently in the consistent fashion, also in the theory of graphs make no difference. Consequently, even though technically or physically a chess knight moves in the L-shaped, we connect the vertices or the nodes of this graph with a straight line like so. 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, 4 is connected to 5, 5 to 6, 6 to 7, 7 to 8, and 8 to 1. Now, from the geometric standpoint, this particular shape is called an octagram. I'll write it down over here. Octagram. But we know that 2 graphs are considered isomorphic if, in some sense, let me cover the names of the companies that made this ball so you guys don't think I'm advertising something. If these 2 graphs can be morphed continuously in some sense, one into another, by manipulating the edges and the corresponding adjacent vertices in such a way that no single connection between adjacent vertices is broken or ripped apart, then, for example, as we showed in this example, just to demonstrate, for example, why are these 2 graphs isomorphic? Well, again, the number of vertices in these graphs are the same. We see all the corresponding adjacent vertices remain adjacent between 2 graphs, but the vertices of the graph shown on the left, named B and E, simply swap like so with respect to this graph, for example. In other words, if we take this graph and model the vertices B and E with 2 balls connected with a string, then if we flip these guys around, then we will obtain the graph shown on the right. And conversely, if we begin with the graph shown on the right and model its vertices with the balls like so connected with a string, then we can simply flip them around, and then we will obtain the graph shown on the left. And that is in some sense, visual demonstration of the fact that how specifically in the plane the nodes connected with an edge positioned doesn't really matter, as long as the connection between the vertices remain the same. And as we explained earlier, the adjacent vertices in one graph remain adjacent in the other. In contrast, in this pair of graphs, no matter how we manipulate, for example, the nodes D and B connected with an edge over here, like so, we will not be able, for these 2 guys, for example, we will not be able to inject another vertex A or vertex C over here without ripping the connection between these 2 nodes, and conversely. For example, in this graph, the nodes A and B are connected with an edge. No matter how we manipulate these 2 nodes or these 2 balls connected with a string, we will not be able to make sure that the node D now connects to the node A. What that means in our case is the following. Let's concentrate on the node number 2. This node connects to the node number 1 and node number 3. And its symmetrical friend, vertex number 6, connects to the vertex number 7 and vertex number 5. If we are to take this particular octagram and carry it over here without the squares obscuring our view, then we will have the following arrangement: 1, 2, 3, 4, 5, 6, 7, 8, and back to 1. And imagine that these guys are connected as shown over here. 5 to 6, 6 to 7, 7 to 8, and 8 to 1, like so. Just as we demonstrated a few seconds ago, we know that this particular graph can be continuously transformed into a different version of itself that will still be essentially the same graph. And the way we do it is by, for example, taking the vertex number 2 and flipping it into the position occupied by the vertex number 6, and at the same time we take, for example, the vertex number 6 and flip it into the position that was occupied by the node number 2. In that case, we will have the following arrangement. If we erase these guys and these guys, then we will have the vertex number 2 over here, vertex number 2, and we'll have the vertex number 6 over here. This will be vertex number 1, and I'll show these connections: 1 and connects to 2, 2 connects to 3, and 5 connects to 6 as it used to, and 6 connects to 7. Then we can also concentrate on the vertices named 8 and 4 shown over here. And in this particular version of the graph, we see that with the thin line I show the connection 4 to 5 and 3 and 8 to 7, 8, 1. It should now be evident that a continuous, or in some sense isomorphic transformation, will take the node number 8 into the position occupied by the node number 4, and it will take the node number 4 into the position occupied by the node number 8. But remember that when that transformation takes place, that node, for example, 4, will take its connection with the node 5 with it. In other words, now the nodes 5 and 4 will be connected over here anyway, like so. Let me erase this connection here, and this connection here, and this, and show the new position of the edges. This one will be node number 4. This will be node number 8. And this will be connected like so: 4 connected with 5 and 3, and 8 connected with 7 and 8. Now let us take a look what is going on with this new arrangement. In the new arrangement, our names of the vertices go sequentially: 1, 2, 3, 4, 5, 6, 7, 8. Let me make these guys a little bit brighter. 8, this is 5, this is 4, this is 3, and this is 1. And if we place our knights that are positioned on the top, the 2 white knights, over here into the squares number 1 and 7, and if we place our black knights positioned in the squares number 3 and 5, like so, over here, then let me mark the nose a little bit brighter, make it brighter. Then what do we see? Then we see that in order to solve this problem, instead of haphazard or random motion of the knights over square with no solid idea behind it, all we have to do is move our knights, in this particular case counterclockwise, along essentially a circle. Let me show this with this will be essentially a circle. Remember again the specific shape of the edges that connect to corresponding vertices of a graph in the theory of graphs doesn't matter. So essentially we have a circle, and because every next position for every knight is open, for example, this knight can jump into position 2, this knight can jump into position 4, this guy into 6, and this guy into 7. All we have to do is carefully move these knights one at a time until they swap their positions and the white knights over here occupy the nodes named 3 and 5, and the black knights occupy the positions or the nodes numbered 1 and 7. Now, let us carefully execute this particular solution step by step. Before we do that, however, let us go over the mechanics of the transform and conquer problem solving approach. How did we set up a transformation that we think will help us come up with a straightforward and easy in some sense solution of this problem? Well, we numbered the squares of the given chessboard in a knight tour fashion, going in this particular case clockwise. Next, technically we took an abstract notion known as a mathematical knife, and we cut this particular board into 9 squares, of which the middle square is actually unreachable and we don't really care about it. But when we transform the original graph into its isomorphic copy shown over here, technically we actually moved the corresponding squares of a chessboard with this particular nodes, and in theory I should really draw the corresponding squares over here, but I will not do that in order not to make a mess over here. You guys understand that this particular graph represents a disassembled chessboard in this view. Now, is this transformation reversible or invertible? Well, of course it is, because just like we stretched or unstretched these particular nodes 2 and 6 and 4 and 8, we can stretch them back in, swap the positions of the nodes 2 and 6 into the position shown over here, and swap the nodes 4 and 8 into configuration shown over here. This will also bring the corresponding squares of the board into the original position, and using the inverse of a mathematical knife, so to speak, we use another abstract notion, a mathematical glue, to glue these pieces together into the original 3x3 board. Does this candidate transformation respect or preserve the technical essence of the original problem? The answer to that question is also yes, because even though here on a circle, so to speak, our chess knights or our chess pieces move one position at a time like so, these positions are logical or virtual, because still, remember, this transformation is reversible. So on an actual chessboard, our chess pieces move in a completely legal and allowed fashion by jumping the way they are supposed to jump. Lastly, does this transformation afford or gives us a tactical advantage that allows us to solve this problem in a more straightforward or easier in some sense way? The answer to that question is also yes, because all we have to do in this case is not haphazardly jump around the board, but carefully move all the chess pieces one at a time, because the next position for each chess knight over here is open and can be carried out. As such, at first, we will use a maneuver that is popular in combinatorial analysis, and our original, remember that I earlier mentioned that our original chess knights are anonymous, meaning that we do not really distinguish between left and right for a given color, and we think that they are indistinguishable in that sense. But purely for tactical purposes of keeping track of who does what and what goes where, we will number, or we will name, or we'll make our chess pieces unique by, for example, naming these two white knights as sub L, sub R, L for left, R for right, and in the same fashion we will make our black chess knights also unique or distinguishable by subscripting them with L for left and R for right. We have two sets of isomorphic chess pieces, and we will shadow or trace the motions of the chess pieces over the transformed or easier setting on the left with the actual motion of the chess pieces on the board that are in theory supposed to be difficult. As such, we begin. For example, we move the white knight marked as L from the node number 1 to the node number 2 in the transformed setting or in the easier setting, and we shadow that move with the jump of the knight on the actual board over here. That move is completely legal. That square is open, and this is also how symbolization in mathematics comes about. We may record this motion, for example. This will be the white knight that goes from 1 to 2, for example. Again, there is no ambiguity because there is only one chess knight positioned at the origin square numbered in the parentheses. W1 to 2 means that the white knight that positioned at the node number 1 jumps to the node number 2. Then, for example, the white knight with the subscript R jumps to the, he jumps over here to the node number 8 on the transformed orbit, and on the actual board he jumps over here into position 8. We record this guy as white from 7 to 8. 7 to 8. Then we grab the, for example, black knight with the subscript L, and he jumps from 3 to 4 like so. And on the actual board, this guy jumps from 3 to 4 over here. We record that move with, like we'll put a comma here, from 3 to 4. And another guy, we anticipate him already. He will jump from 5 to 6 like so in a transformed or simplified setting. And on the actual board he will jump from 5 to 6 like so. We'll record that move. Black knight moves from 5 to 6, and we'll mark this. The total cost of this cycle is 4 moves shown over here. Once we went through this 4 cycle, we execute the next one. The white knight marked with the subscript L jumps from the node named 2 to the node named 3, and we record it over here from 2 to 3, comma. Then the next guy, the white knight named with the subscript R, jumps from the node number 8 to the node number 1. Let's put him right here. White goes from 8 to 1. On the actual board, the guy who went from 2 to 3 went from 2 to 3 over here. We'll trace this guy. And the guy who went from 8 to 1 goes from 8 to 1 over here. Now, the next move will be by the black knight with the subscript L from the vertex 4 to the vertex 5 over here. We will record this guy black from 4 to 5, and this guy, where is he, from 4, he jumps to 5 on the actual board over here and completes this 4 cycle, the motion of the knight with the subscript R from the node named 6 to the node named 7, like so. And we record this guy black from 6 to 7. Again, this is 4 moves from 6 to 7, and in the intermediate positions over here, we can see that our knights are aligned this time vertically as shown over here, and we keep going. For the next 4 cycle, we take the white knight with the subscript L and move him from the node named 3 into the node named 4. So white knight goes from 3 to 4, from 3 to 4 on the virtual orbit, and on the actual orbit he jumps from here to here. We'll keep this guy here. Next, the white knight with the subscript R jumps from the node 1 to the node named 2. We record him 1 to 2, and this took place on our virtual board. On the actual board it will jump from 1 to 2 over here, like so. Next, the this will be the black knight with the subscript L, moves from the node number 5 to node number 6, like so. We record him black from 5 to 6 on the virtual board, and on the physical board this guy will jump from 5 to 6 over here, like so. And this 4 cycle will be completed by the motion of the black knight with the subscript R from the node number 7 to the node number 8, like so. We'll record this will be black from 7 to 8. This again will cost us 4 moves from 7 to 8 over here, like so. And in this particular case, we see that the knights are positioned in an interesting diagonal formation, and we already anticipate that on the next 4 cycle the problem will be solved and the game will be over. Let's see if that's the case. We begin this 4 cycle with the motion of the white knight with the subscript L. He jumps from the node number 4 to the node named 5. So white goes from 4 to 5 on the virtual board. On the physical board he goes from 4 to 5 over here, and we already feel that this particular knight is in his home place. That's the destination square for this guy. He will rest there for now. Next, the white knight with the subscript R jumps from the vertex named 2 to the vertex named 3. Let's put this guy over here. From 2 to 3. That was on the virtual board, and on the physical board it will be jumped from 2 to 3 over here. And right now the intermediate position feels a little funky, what's going on here, but we feel that the white knights are already in their destination or their home squares. The game is over for them. They can go drink some water and eat some food. But 2 more moves left. The black knight marked with the subscript R jumps from the vertex named 8 into the vertex named 1, like so. So black knight goes from 8 into 1, and that was on the virtual board. From, where is this guy? On the physical board, this guy jumps from 8 to 1, like so. This guy goes here, and we already see that this knight is in its home square. The last move is by the black knight marked with the subscript L, and this knight jumps from the node named 6 into the node named 7, like so. We will mark this guy from 6 to 7. This is also 4 moves. That was on the virtual board or disassemble board. The actual jump on the physical board will be from 6 to 7, like so. It's a little jump, it's open. Let's keep this number visible, like so. And we rearranged the anonymous positions of the anonymous knights as was requested. Now we swapped the positions of the white and the black knights as requested. And what is the cost of this particular algorithm? Well, it is straightforward. It's not really mathematics. Now is computational calisthenics at best, or arithmetic. The cost of this algorithm is 16 moves, and we claim that 16 is the smallest number that cannot be improved by legal means, precisely because over the set of natural numbers or over the set of positive whole numbers, there are no extra numbers between the immediate neighbors. There are no extra positive, whole positive numbers between 1 and 2, between 2 and 3, 3 and 4, and this particular manipulation represents the smallest number of moves possible, and that number is 16. Now that we completely solved the problem at hand, we see that the formerly or previously indistinguishable or anonymous chess pieces actually trade places in both cases. The, for example, white chess knight that was left in the top row became the right one with the subscript R, it really should be, and the white knight that was previously in the right position over here now took the left position over here. But in one of the best traditions of combinatorial analysis, now that we solved the problem and we understand what is going on, we make the distinct or distinguishable objects over here back non or indistinguishable again. We erase the subscripts, we place the original chess pieces as shown over here, and over here. We erase our scaffolding, all this graph theoretic material is gone too, and we present a solution reported over here. Also, the folks who are into chess way more than I am and who take it way more seriously, they can object to my notation, but in my defense, for example, I can say that we can make the W's over here again distinct by slugging in the right index over here, which was here. Probably this guy is left, this guy is right, and so on. But as the German mathematician Karl Gauss used to say, what we need more of is not a notation, or we need more of good notions. Now, this problem is actually quite interesting and quite beautiful for at least 2 reasons. The first such reason is historical. According to my fact-checking capabilities, the first time that this problem was published, at least in the Western literature, was in the year of 1512. That is more than 500 years ago. And again, to the best of my knowledge, you guys are more than welcome and should really verify what I'm saying here, but According to my information, in one of the first publications more than 500 years ago, this particular problem was wrapped into the language of frogs jumping on mushrooms that are positioned correspondingly, and that is how the title of this episode came to be. The second reason why this problem is quite beautiful and quite hefty mathematically is because this, in our sequence, this was problem number 8. It means that the previous 7 problems that we solved, we also used one and the same transform and conquer problem solving approach. We solved each such problem very slowly and thoroughly. We explained every step. We investigated and analyzed the 3 fundamental properties of each and every successful candidate transformation that unlocked a beautiful and an elegant solution of the problem. But with this problem, we see that verbally or descriptively, this problem is very different from the previous 7 problems that we solved, and these problems had to deal with the first problem dealt with a wholesome and a broken sphere. The next 6 problems had to do with regular polyhedra. And despite the fact that the problem statements feel or sound different, all these problems nonetheless were solved using one and the same problem solving approach, to which I refer as transform and conquer. And that particular situation tells us that pretty much each and every worthy or interesting mathematical problem consists or packaged into 2 pieces. One such piece is something that doesn't change, and that something that doesn't change represents the technical essence of this particular problem, and something that does change, and whatever material does change does not affect the technical essence of the problem, or something that remains invariant with respect to the language into which this essence is wrapped. Consequently, this is one of the awesome or beautiful parts of mathematics. When we cast our eyes onto a problem statement in mathematics, we should try to see this situation through and try to unpackage this package, so to speak, and separate the technical essence of the problem at hand from something that can vary and does not really affect the technical essence, or something that does not change. And then we should actually fight the fight with the essence and not with its verbal variation from one problem to another. In the next problem, or in the next challenge that I'm about to give you guys, you will have a chance to discover on your own a different problem solving approach. I will not tell you what it is in this episode, but I will obviously explain it in the next episode. But I would like you to take the opportunity with the next example and see if you can uncover this more abstract situation that goes on with that problem on your own. In our next challenge, the problem S1M9, we're given 100 lights or 100 light bulbs arranged on a garland, like so, for example. And with this garland of lights, our friendly dwarf performs the following manipulations. On his first walkthrough, the dwarf turns each and every light on. On the second walkthrough, the dwarf changes the state or flips the state of every second light to its opposite. What does it mean to flip or to change the state of a light bulb to its opposite? That means that if the dwarf sees the current light as on, then it will turn it off. And if our dwarf sees the current light as off, it will turn it back on. Next, on the third walk through the garland of lights, our dwarf flips or changes the state of every third light to its opposite. On the fourth walkthrough, the dwarf changes or flips the state of every fourth light bulb to its opposite. On the kth walkthrough, our dwarf flips or changes the state of every kth light bulb to its opposite, and so on until on the last or 100th walkthrough, the dwarf changes the state of every 100th light to its opposite. The challenge or the question in this particular problem is then to figure out which lights will be left in the on state, will be shining brightly after the end of the 100th walk through. Those of our viewers who have been watching the episodes presented on this channel in sequence already noted that I use very simple language in order to explain how a particular problem-solving approach works. For example, in our first 7 problems, all that is needed to solve this problem was a pair of scissors, a straight edge, a compass, and a sheet of project or heavy paper. In other words, the language in which the problems are wrapped does not really require years and years of dedicated and highly specialized training. That is so because I think that in order to demonstrate an idea or an approach in mathematics, the simplest possible formulation or the simplest possible problem that exposes the essence of what is being explained is enough. But once that technical essence of the approach at hand is understood, there are literally no upper bound on the complexity of the problems to which this particular problem-solving approach can be applied. In this particular case, we do not really need anything or any materials, just the general situational awareness and some amount of paper to experiment with the flipping lights on and off. This is it for this episode. Thank you very much for staying with us. Thank you for your time. I'll see you in the next episode, in which I will dissect the solution of the problem S1M9.